Good morning, everyone. We'll start shortly. As usual, please write your name on the chat to let me know you're here. And we'll start a new chapter today, chapter 5. And it's let's see, labeled. So we saw the intermediate value property, and now chapter 5 is about the derivative. And the derivative is an object that most of you are familiar with. So as it is customary with any of the chapters in the book, we'll actually start with a little introduction. This section 5.1 has no exercises, but it has a way to motivate the rest of the section so that you can get an idea of what is it that we're trying to do. And with respect to the derivative, you need to understand that we're not going to be doing what you had done in the 150A, 150B sequence. So we're not going to spend our time doing applications of the derivative, figuring out absolute maximums, absolute minimums, inflection points, where the function is increasing, decreasing, sketching the graph of the function, doing optimization problems. All of those are applications of the derivative. What we're going to be mostly concerned here in chapter 5 is about understanding, really what the derivative is and how is it substantively different. The concept of a function having a derivative, how is it different from a function being continuous, right? And so we'll start talking a little bit about that to begin with. So let me switch to the screen. And as I was telling you, so first we'll start with 5.1. And 5.1 is a bit an introduction, like I was telling you. So it's called Are Derivatives Continuous? And that's the question we're going to try to go over. So to begin with, we're going to go over this with more detail as soon as we get into 5.2. But I wanted to let you know that I'm well aware that you all know already what the derivative is. So we will informally talk about it today, right now at 5.1, and with the understanding that we're going to define it properly lately, okay, very shortly. So what is the deal? So we have a function, like this, y equals f of x, right? And if we want to talk about the derivative, say here at a point C, right? Ordinarily, what you do, what you should have learned in your 150A class, is that you're going to consider a point really close to C. And right now, I'm not going to draw it as that really close. I'm going to put it over here, X. And you're going to look at this line, the line that goes through these 2 points. And that's a secant line. And you're going to figure out what is the slope of that line. And the slope is, well, the rise divided by the run, correct? And the rise is f of x minus f of c, right? How the difference between the height of this point and the height of that point. And the run, well, from c to x, so it's divided by x minus c. And then the understanding to try to come up with the meaning of the derivative was the problem we were trying to answer in 158. The problem was to find the slope of the tangent line. And that, of course, first we need to figure out what the tangent line is. And here the idea is you're going to let this point now get closer and closer to C. And when you do that, these lines are going to become closer and closer to our idea of what we think should be the tangent line, which is this bolder one that I'm drawing right now, right? The tangent line. tangent line. And then, because this sequence of black points is getting close to C, we define the slope of the tangent line as the derivative at C with this limit. Okay, and then, well, we learned ways on how to calculate it and so on. But the questions now we want to do is, what we want to figure out is this, right? This thing over here. Are derivatives continuous, right? That's what we are concerned about right now. And very quickly you learn that if a function has a derivative, then the function itself is continuous. We'll see that in a moment. But that's not really what this question is asking, right? So I want to present a few examples to you of functions that we know are special or different, right? And this will be as an important examples for all of this section. Important examples. Let me, we've seen already a couple of them, and it will be these functions. The functions, we call them GN, the book does, and they're like this. They're x to the n, sine of 1 over x, if x is not 0, and 0 if x is 0. All right? So in particular, you remember this one. So we call g0 of x. We've seen this one before. That's just simply sine of 1 over x if x is not 0, 0 if x is 0. And this was an example of a function that was not continuous, right? This function, not continuous at 0. Let me show you a picture. See, one of the few advantages that we have of having class like this is that I can actually now show you things like this, right? So this is, let me go back. So this is a better drawing of this function sine of 1 over x. And here you can appreciate very, very easily the reason why it's not continuous at 0. It's not continuous at 0 because it oscillates like crazy from -1 to 1, -1 to 1 as we get close to 0, right? And this d that you see here, this slider, what it does is just zooms. It zooms near 0, right? So if you want to see closer, I can just get closer, and it's right now it seems like it's not doing anything because when I lift the button, then it recalculates the graph of the function, right? So as you can tell, it doesn't matter how much I zoom. In fact, it seems to get worse, right? The closer I get, the more up and down you see, right? Because it's actually oscillating faster and faster as we get closer and closer to 0. So right here near 0, not continuous, right? This function is not continuous. Okay, now I actually, if you see right here at the top, right at the very top, you can see that I actually define this function in general, right? I can plot x to the n sine of 1 over x. So I can show you the other iterations. And I want to look at G1, right? So let's change this one to 1 and back away like we were maybe at the beginning. Okay. So that one that you see over there, that's the function G1. So this is x times sine of 1 over x. And I'm going to get closer because this part on the, I mean, I really care what's happening near 0. So I should probably get right there. That's a good point to look what's going on. So what's different now is that we still have this oscillation back and forth near 0. But now when we multiply by x, those oscillations are getting smaller, right? They're getting smaller. So this graph is oscillating now. Instead of oscillating from -1 to 1, now it's oscillating from -x to x, right? So you can even sort of see those lines right here, right? You can sort of see, if you look at the tops and the bottoms of the oscillations, they almost look on a line, right? And that would be correct. This would be the line y equals x, and this would be the line y equals -x. So it oscillates between those two lines. And then we may ask ourselves if this is continuous at 0, and it is. We proved it a few classes ago. So we know that this function g1 is it has a derivative at 0. So from before, we know that. I mean, not that it has a derivative, it is continuous. G1 prime at 0 exists. And it actually equals 0, right? Now again, I'm saying it wrong. Not the derivative, the function is continuous at 0. So we know that the limit of G1 when x approaches 0 is 0, which happens to be G1 of 0, right? And that was easy because this limit was x times sine of 1 over x. So check your notes. We did it when we started talking about continuity of functions, all right? But what about the derivative? That's the next question here, right? What can we tell about the derivative? So let's go back to the page. So this is what I was telling you. So we knew from before that this limit is 0. So this function approaches 0 and it looks like it's approaching 0 from the picture, right? Those oscillations are getting smaller and smaller, and they seem to be getting close to 0. Now, if we wanted to talk about the derivative, all right, so let's try to calculate the derivative. So first, let me write G1. So here's G1. G1 is x times sine of 1 over x if x is not 0, and 0 if x is 0. So what would be G1 prime? Well, at least, I mean, again, right now I'm assuming that we already know the things I know you know for derivatives. So at least if x is not 0, we can find the derivative by simply, well, doing the derivative of this, right, of x sine 1 over x. And how do we do that? Well, we first apply the product rule and then the chain rule, right? So it will be the derivative of x, which is 1 times sine of 1 over x plus x times the derivative of sine of 1 over x, which is cosine of 1 over x times the derivative of 1 over x, which is -1 over x squared. And that would be if x is not 0. And if x is 0, we don't know. Right? Let me put a question mark here. So we don't know. We would need to do the limit, right? So let's try it. Let's go back to what we already know is the definition of the derivative. It's right here, right? We need to do f of x minus f of c over x minus c. So let's try it with 0. So let's try to get G1 prime of 0. All right? How would we do it? Well, is the limit when x approaches 0 of G1 of x minus G1 of 0 over x minus 0. I just copied the definition, right? I haven't done anything here. Now, let's plug what this represents. What is G1? G1 is x times sine of 1 over x. And I can safely plug that because x is approaching 0. X is not equal to 0. X is getting close to 0. So the part of the definition I should use is this one, right? The one on top. Minus, when we get to 0, the answer is 0. And we're dividing by x. So from here, you can tell that we can cancel this x. So the new limit I get is simply sine of 1 over x when x approaches 0. And what do we know about this limit? It doesn't exist, right? Yes, thank you, Ashot and Petrus, right? This one does not exist, right? Does not exist. So what did we just discover here? Well, this function g1 is a function that has this property, is continuous, right? Because look over here, right? When we approach 0 of the function g1, we did get g1 of 0. So it's a continuous function, but it's not differentiable, right? So g1 is differentiable, but not continuous at 0. So g1 of x is continuous on the entire set of real numbers, but not differentiable. That's just a fancy word for having a derivative at 0. Okay? All right. So, and the discontinuity is one that we cannot really fix, right? It really is an essential discontinuity, to give it a name, although, well, we'll precisely define that, as I was telling you, in later when we keep going. So so that's the story with G1. Let's do one more. Let's talk about G2. So what about G2? So let's write G2 here. So G2 is now x squared sine of 1 over x if x is not 0, and 0 if x is 0. Okay, and let's go to the picture again. So let's show my little app that I wrote in Mathematica, and let's just move this to 2. All right, and it still has this oscillation back and forth, as you can tell. So it's still going up, down, up, down, up, down. But now, and this should make perfect sense, now this thing is oscillating with the top parts over here are a parabola, the parabola x squared. Let's see, maybe I can, let's see if I can do this. It'll be difficult, but I can try it. So this, yeah, this is not the best. Oh, not bad actually. All right, more or less that one over there. That's a parabola. It's a parabola x squared. And if you draw the one and touching the bottom parts over here, that will be the parabola negative x squared, right? So this function oscillates between those two parabolas, between negative x squared and x squared. So just from the look of the function, it seems that it's going to be continuous at 0 again, like G1, right? It seems like this function will be continuous. Let's actually look closer. If I zoom in, right now my parabolas are all crooked, right? So if I zoom in, as you can tell, I'm still going between the two parabolas, and the oscillations are wild. I mean, are more up and down, up and down, up and down, up and down, right? It looks more elaborate there, right? We have, it's like we're compressing the oscillations. And it makes sense, because when you approach 0, 1 over x grows. It grows too quickly. So the sine function is going through values quicker, right? So it's oscillating faster and faster. So let's analyze the derivative of this function. Let's see if this time the derivative exists at 0. Okay, so let's go back to the page. All right, so what would be the derivative? Well, first, we can check that it is continuous, but it will be. I'm going to bypass that part. That's easy. So let's try to come up with the derivative. So what would be G2 prime? Well, again, if x is not 0, we can simply follow our rules. So it would be the derivative of x squared, which is 2x, times sine of 1 over x, plus x squared times the derivative of sine of 1 over x, which is cosine of 1 over x, times the derivative of 1 over x times the chain rule. So it's negative 1 over x squared. And this time I'll simplify this. This x squared cancels with this x squared. So this is actually 2x sine of 1 over x minus cosine of 1 over x if x is not 0. And we don't know if x is 0, right? So let's try to figure it out this time. So how can we figure it out? We go by the definition, right? So what would be g2 prime of 0? It should be the limit when x approaches 0 of g2 of x minus g2 of 0 or x minus 0. That's the definition. Now I'm going to copy what g2 is. And g2 is this function over here. So it's x squared sine 1 over x minus 0 divided by x. So this is the limit of x sine of 1 over x. And I don't know if you remember this limit, but this limit is actually equal to 0. So this limit equals 0. If you don't remember it, I'll do it again. No problem. So how do I know this limit is 0? Well, because give me an epsilon, and I can set delta to be equal to epsilon. It's as easy as that, believe it or not, right? Then if the absolute value of x is less than delta, then this happens. X times sine of 1 over x. Well, sine is always less than 1. So this is the same as x times absolute value of sine of 1 over x. And the sine is always less than 1, so this is less than x, less than or equal. And I know this is less than delta, but delta is equal to epsilon, so this is less than epsilon. So that's it, right? For an arbitrary epsilon, I gave you a delta, such that when this happens, this x sine of 1 over x is less than epsilon. So that's it. This means that the limit when x approaches 0 of x sine of 1 over x is 0. So this function has a derivative, and it's 0, right? It has a slope of the tangent line, believe it or not, right? Even though it oscillates like crazy, right there at the point where all the oscillations are converging, we do have a tangent line, and it's a horizontal tangent line, believe it or not, right? So this function is derivative. I'm sorry, this function has a derivative. So this function g2 is differentiable everywhere. So here, instead of the question mark, we should replace that. And it's actually 0, right? The answer is 0. Now, what about the function, the derivative function? So this function g2 prime, is this function continuous? Because that was the original question, right? So here is really the question we were asking over here. So are derivatives continuous? And I understand that question in the following way. If we have a function which is the derivative of something else, is it continuous? So like this, g2 prime is the derivative, right? Is the derivative of g2, this g2 prime function. So now the question is this function continuous? Is g2 prime continuous? That's the question we want to check, right? And well, let's see. If you look over here, when x is not 0, well, yeah, it's gonna be continuous, right? Because we already know all of these functions are continuous. 1 over x is continuous, sine is continuous, cosine is continuous, x is continuous, and when you do composition, addition, or multiplication of continuous functions, you get something continuous. So when x is not 0, no problem. The issue is at 0. So let's check continuity at 0. So the answer, the partial answer here is yes, if x is not 0. What about 0? Well, let's check 0. So for that, we need to do this limit when x approaches 0, right? And what's the deal? Well, the deal with this limit is, let's go back to what g2 prime is right here. See, the problem here is that this part well, let me write it here. Let me rewrite. So I'm just going to copy this function in the bottom part that you don't see right now, but because we want to calculate this limit. Here we go. So this is the limit we want to do, right? And this part, the first one, we already know goes to 0, is the part that I show you with epsilons and deltas. So this part goes to 0. But what's going to happen with the cosine of 1 over x, right? The cosine of 1 over x is going to be the same as sine of 1 over x, which is a question I asked you before, right? The question that both Petros and Ashot answered. The limit of sine of 1 over x does not exist. It oscillates like crazy. Well, the same happens with this one. This limit doesn't exist, right? Does not exist. So that means this limit, the overall limit of G2 prime, doesn't exist. So this limit also is a DNE, does not exist, which means this G2 prime is not continuous, right? So it's not continuous at 0. Not continuous at 0, right? So again, we got an example of a function that has a derivative, but the derivative is not continuous, right? The derivative failed to be continuous. Okay, and the type of discontinuity, so it failed because we had a discontinuity of oscillating like crazy. So let me write that down. So G2 is a function which is differentiable, but the derivative is not continuous. But the reason the derivative is not continuous is by oscillation of up and down, right? So the reason is by arbitrary oscillation. And that's kind of complicated, right? It's a complicated way of thinking about a discontinuity. So here is now the question. Can we have a function that has a derivative, and the derivative is not continuous, so kind of like this one, but instead of being not continuous because of this crazy reason, I wanted it to be not continuous because it has a jump, right? Jump discontinuity, where you have a different value from the left as you have from the right. So that's now my new question. Is there a function? Is there a function such that its derivative exists and the derivative has a jump discontinuity? All right. So for example, imagine that the derivative is something like, so let's e.g. right here, imagine that we want something such that the derivative is, so here's a simpler question. Is there age such that the derivative is -1 if x is less than 0 or 0, and 1 if x is greater than 0, right? Seems easy, correct? So this is the derivative. Now, can you give me the function that makes this work? Okay, and Justin says the absolute value, and that almost work, right? So let me write something here. If you are thinking h of x equals absolute value of x, right? This is x if x is greater than 0, and negative x if x is less than 0. This one almost works, right? See, if x is greater than 0, you get 1, good. And if x is less than 0, the derivative of negative x is negative 1. So you get, you almost get it. The problem is 0, right? Because what happens with this one? What is h prime? What is h prime of 0? Well, it should be this limit, right? The limit when x approaches 0 of h of x minus h of 0 over x minus 0, which is the limit of absolute value of x minus absolute value of 0 over x minus 0, which is the limit of absolute value of x over x. And and I can show you this limit doesn't exist in a very easy way. Pick a sequence that approaches 0 with positive numbers, and this will be 1. But if you pick a sequence with negative numbers, this will be negative 1, right? Or in other words, that's the other way we know, is this function absolute value of x has a sharp turn, right? If we draw it, it looks like this. So it's continuous, that part is good, but it has a sharp turn right there. So it goes from being in a negative 1 to positive 1, right? So sharp corner right here, which makes this limit does not exist. So this function does not work because this is not the derivative, right? We fail at 0. And this is a weird question, right? I mean, so this one doesn't work, but can we find another one that maybe works? I won't tell you the answer just yet, but it's a great question, right? Can we have a derivative with a jump discontinuity? That's essentially the question. Are there examples of functions like that? Derivatives that have a jump. Okay, so this is the end of my intro, right? This is this section 5.1. As I was telling you, we were sort of, I mean, we didn't properly define the derivative yet, and yet we were doing calculations and everything. So now we're gonna take a couple of steps back, and we're gonna start from the very beginning. So this will be now section 5.2, and we're gonna start from the very beginning, meaning we're going to talk about the definition, right from the get. So here we go. Now we're doing it the official way. So we're starting with definition 5.2.1. Says the following: let g from a to r be a function defined on an interval a. So our domain is an interval, all right? Given a c in that interval in a, the derivative of g at c is defined as g prime of c equals the limit when x approaches c, g of x minus g of c over x minus c. All right, so there you have it. We were sort of using it already, and so that's it, right? And okay, so first we have, let's do a little example, right? Some that we can actually calculate. So we'll start with example 5.2.2. We're gonna calculate the derivative of x to the n. So if f of x equals x to the n, for n a natural number, then f prime is nx to the power n minus 1, right? The traditional one that you use all the time. the so-called power formula. And we use that as the basis to take the derivative of almost, well, to begin with polynomials and then rational functions and so on. So why is this true? And maybe you've seen this in calculus. I certainly do it for my calculus students. It's not that difficult to show this. See, all I need is this little factorization. So we go by the definition. So what would be G, not G, in this case, F prime. By definition, F prime of X, F prime of C, let's do it at C. F prime of C is the limit when X approaches C of F of X minus F of C divided by X minus C. And this is X to the N minus C to the N over X minus C. And the trick here is to factor X, this difference of N powers. And that difference of N powers factors as follows. Factors as X minus C times X to the N minus 1 plus, how should I write it? C, yeah, plus Cx to the N minus 2 plus C squared X to the N minus 3 dot, 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 right? And then the pattern reverses. So let me write the last one will be C to the N minus 2X and then C to the N minus 1. Okay? And so this is like the difference of squares formula. So let me make a little. So if you've never seen this one, it's easy to verify. Just cross multiply. So just multiply it out. Do the multiplication, and you'll see that everything cancels. You get a telescopic sum, and the only two terms that survive are X to the N and C to the N. So this is the equivalent of doing X squared minus C squared is X minus C times X plus C. That's the first one. And maybe you remember even the one for cubes, which is X minus C times X squared plus XC plus C squared, and so on, right? You can add more terms. You can, if you do the one for fourth, you will have more terms here. All right, so the good thing about this is that now we can cancel this, right? Because remember, X is approaching C, X is not equal to C, so that limit can be canceled that way. And now we get a limit that we can do easily because it's a polynomial, right? It's a limit where we can simply plug it in because we know it's continuous. Polynomials are continuous, and we have right here a gigantic polynomial. So we are allowed to simply plug X equals C because polynomials are continuous. And when we plug X equals C, we get C to the N minus 1 plus C times C to the N minus 2 plus C squared times C to the N minus 3, etc. And if you notice, all of these are C to the N minus 1s, and there are N of them. So this is N C to the N minus 1. And that's the end of our little example, right? Where we showed that the derivative of X to the N is X is this one, N X to the N minus 1. Okay. Good. So next, let's take a look at this very small and easy. So this theorem I also present to my calculus students when I mean, it's not that difficult at all, but let's write it here. Theorem 5.2.3. It says the following: if G from A to R is differentiable. Differentiable, by the way, means it has a derivative at a point C in A, then G is continuous Let's see. Okay, so we informally call this theorem the differentiability implies continuity. So if a function is differentiable at a point, then it's continuous at that point. Now, don't be confused with the question we were talking about before, right? The question we were talking about before was if we could find a derivative, which was discontinuous with a jump discontinuity, right? That's different. We were talking about the derivative. Here we're talking about the original function. If the original function has a derivative, then the original function is continuous. In the other, we were talking about a property of the derivative. Here it's a property of the original function. All right? Don't get confused. Okay, so how do we prove this? Well, it's easy because all we need to do to figure out that something is continuous is to show that when we approach C, the function g approaches g of c, because in this case, because we have an interval, because we're working with an interval, c is a limit point. And because it's a limit point, we can simply show that the limit is equal to g of c, right? So the best way to do this is, so here's the proof. So suppose g is differentiable at c. That is, this limit exists, right? G prime of c equals the limit of g of x minus g of c over x minus c exists, right? Okay. What do we want to show? We want to show that, so let me write it here. We want to show that the limit of g of x is g of c. And we're gonna do it in a little bit of an indirect way. So here's the limit we're really going to calculate. We're gonna calculate the limit of g of x minus g of c. And I want this to be 0. If it is 0, then we're done because this is a constant. So then if this limit is 0, then the limit I want, I can write it as this limit plus the constant g of c, which would be this one, right? So I just need to show this one is 0. And this is easy to show it's 0 because this limit, the limit of a product is a product of the limits when those two limits exist, right? So we're using the algebraic limit theorem, not for sequences, but for functions. And we prove that with using the one with sequences. And to use it, we need to know, this is very important because a lot of you use it the wrong way. Whenever you use the algebraic limit theorem, you want both limits that you're multiplying to exist. What are the two limits that I'm multiplying here? These two. I'm going to do this one, which I know it exists because it's right here. And this one, x minus c, which I know it exists because it's a polynomial. It's a line, as a matter of fact. So from here to here, I didn't do anything. I just divided and multiplied by x minus c. But here, this is by the algebraic limit theorem. For functions, this is the product of the limits because both limits exist. And the first one is just the derivative of g, and which I don't really care, but this one I care because it's 0. So this is something times 0. Well, it's equal to 0. And because this limit is 0, it follows that the limit of g is g of c. And we are done, right? The function turns out to be continuous. All right. Questions? Okay. Next in our list of things we should do is to figure out all those other properties we have come to know about the derivative. And that's the next theorem, 5.2.4. And it says the following. If you have two functions that are differentiable, let f and g be functions defined on A, an interval, assume both are differentiable at some point C. Then the following nice things happen. One, you do the sum and you do the derivative and you plug C, well, that will be f prime of C plus g prime of C. So in other words, the derivative of the sum is the sum of the derivatives. Two, if you multiply by a constant, you can just take that constant out and do the derivative. This happens for every real number that you multiply by. Beautiful. Three, if you multiply f and g, the answer will still be differentiable. And this is just the so-called product rule, right? It's f prime of c times g of c plus f of c times g prime of c. It's the so-called product rule. Four, if you do f over g, that will also be differentiable most of the time. And the answer will be what I'm writing, which is the quotient rule, provided g of c is not zero, right? Okay, so the classical properties of the derivative that you already know. So we just want to make sure that we can check them, prove them. And properties 1 and 2 are part of your homework, and they're easy, are actually quite easy. So I'm going to do property 3, and also 4 is not that hard. 4 can be done directly. I think 4 is also another exercise. And there's even a different way to do it in exercise 5.2.3. So I'm not gonna prove all of these for you, but some of these are left so that you can get a little bit of practice. But they're easy. They're really more or less straightforward. So let's take a look at 3. So how do we do the product? So first, let's write the definition. So what would be the definition of this if it existed, right? Well, it would be this limit, the limit of the product function. So that's f product g evaluated in x minus f product g evaluated in c divided by x minus c. And that, by definition, is just f of x times g of x minus f of c times g of c divided by x minus c. All right? Okay, and then the issue is, how do we do this limit? It seems like a difficult limit to do, because when I cannot plug x equals c, because then I get 0 over 0, right? It's one of those limits that you need to somehow get rid of the x minus c in the bottom. And that's what makes it a little bit complicated, right? So here is the trick. It's a nice trick. We're just gonna add and subtract something that will allow us to manipulate this. And what we're going to do is we're going to, I write it here. See, I'm gonna write the first term is f of x, g of x. It's all divided by x minus c. And I'm gonna add, put right here the term that I'm going to add. Right, I'm gonna put some term here. It's a little bit like an intermediate term that's gonna help us out. So it will be f of x times g of c. You know, it's like a transitional term. And then because I'm adding a term here, I should better correct that. So you cannot just put things because you feel like it. Well, you can certainly put a 0 anytime you feel like it, right? So this that I did is fine, because I just put this purple term, but then I put it positive here and negative here. So that's a 0. And zeros, it's perfectly fine to put zeros there, right? So we have that. And then what we're going to do is separate this into two limits, if possible, right? So I'm going to combine these two, the first two here, and notice that I can factor an f of x. So that first one is f of x times g of x minus g of c divided by x minus c. And then on the last two, I can factor a g of c. So if I factor a g of c, what I get is f of x minus f of c divided by x minus c. Right? This is my new limit. Okay, and now I'm going to use the algebraic limit theorem because, well, because I know all of these limits exist, right? So why? Well, I know this limit exists because that's the derivative of g, right? And I know this limit exists because f is continuous. I know f is continuous because f is differentiable, and with the previous theorem we proved is that if something is differentiable, then it is continuous. All right, so let me write all of that down. So we know that the limit of f of x when x approaches c is f of c because f is continuous. Okay, I'm just gonna make a list of we knows. Also, the limit of when x approaches c of g of c is g of c because g of c is constant. Also, the limit when x approaches c of g of x minus g of c over x minus c is g prime of c by assumption. And the same for f. Right? So all of these as individual limits exist. So then by the algebraic limit theorem, I have the limit of the product is the product of the limits, and the limit of the sum is the sum of the limits. So right here, that from that equal sign to this equal sign, I can continue, and this will be the limit of this one, which we said is f of c, times the limit of this one, which we said is g prime of c, plus g of c, times the limit of this one, which is f prime of c. And that's the end. And this is by the algebraic limit theorem. And notice that I very carefully checked that all the limits existed before I used that theorem, right? Otherwise, you cannot maybe use that theorem. All right. Okay. Questions? All right. Then comes the next important one, which is also the one we use a lot, the so-called chain rule, right?
Quick question, Professor.
Yes,
for the
go ahead.
One. So for the first line, we wrote that limit of f of x goes to f of c. On the second one, we just have g of c is g of c. Is that supposed to be g of x equals g of c, or it's supposed to be just the way it is?
It's supposed to be the way it is because look over here, we have just g of c, right? So here we don't even use the g is continuous.
I see.
Yeah.
That's why we have the, okay, that makes sense.
Yeah. I mean, it is, well, here's the other thing though, right over here, you may ask, why did you put f of x and g of c? Why not f of c and g of x? Right? And I could have done that, and the proof could have worked the same way. You only reverse the order of f and g. So
Right.
either proof would have worked.
Gotcha, gotcha. Perfect. Thank you.
No problem. All right, so chain rule. Oh, forgot the numbering. The numbering is 5.2.5. And here's what it says. It says that f from A to R and B and G from B to R satisfy that the image of A is inside B. So the composition first F and then G is defined. If F is differentiable at C, some point in A, and G is differentiable at F of C, at the image, then the composition is differentiable at the point C, and with the derivative being equal to the derivative evaluated and f of x times f prime of x. C, this should be C. The derivative at C is like so. Okay. So the traditional chain rule, right? The derivative of the outer function evaluated at the inner function times the derivative of the inner function. And see, this one is, so there is a very straightforward idea of how to prove it. So let's start with the idea. And there is just a little bit of a difficulty here. So this idea I actually presented as a proof when I talked to my 150A class, but it's not really a correct proof, and I'll tell you in a moment why. So the idea would be to just try to write down the limit, right? So what is the G composed with F at C? Well, it would be the limit when x approaches C of G of f of x minus G of f of C divided by x minus C. Then that's the limit we want to show exists, and it equals this statement over here, right? And here's the idea. The idea, and it's a simple one. The idea is to multiply and divide by f of x minus f of C. And this almost gives it away if you think about it, right? Because look, if you have it like this, then this looks like the derivative. This looks like f prime of C, right? This looks like this one. And this looks like that one, right? I mean, look, is the derivative of G prime. So it should be the limit when you approach f of C, right? So, and you're approaching f of C with these numbers, f of x minus f of C over that one minus that. So there's only one little difficulty, right? And here the difficulty is that in general, when you do this limit of the derivative, x approaches C, x is never equal to C, right? X is getting close to C, but it's not equal to C. And over here, f of x will approach f of C because f is continuous, but it is possible that f of x equals f of C many, many times as it gets close to C. So here, that's the problem. So the problem is, here is the problem. F of x may be equal to f of c even when x is not equal to c, right? And that's an issue. It's an issue because then we cannot use this, that this limit exists. This limit may not exist. We may be dividing by 0 when we get really, really close to this number over here. So it's the right idea. It gives you the right idea of how to do the proof, but it's not a correct proof, right? It's only a correct proof if you know that your function f is never equal to f of c. So if you have something that is increasing, for example, if you have a function f that is increasing all the time, then this proof will work. Then this would be a valid proof. But you don't want to put restrictions on the theorem when the theorem works without restrictions. So we need to go around this. And the way to go around it is to create a sort of auxiliary function. All right. And so that's what we're going to do. So here's the right proof. Proof. So we'll fix the problem by using an auxiliary function. We use an auxiliary function. And here's our function. So here's what we know first. So first, notice that this is really what we want to use. We want to use that G prime evaluated at f of c, right? So this appears somewhere over here. We put the statement again. It appears right here, right? So what is that? Well, by definition, this is the limit. And I'm going to use instead of y, if instead of x, I'm going to use y. When y approaches f of c, of what? Well, of the function g evaluated at y minus g evaluated at f of c, because this is the derivative in f of c, divided by y minus f of c. So that is correct. So this is good. It's just that this is the fact that the derivative at g prime is differentiable at f of c, right? It's right here. What is it? And g is differentiable at f of c, right? So I just wrote what that means. And this suggests to us what should be our auxiliary function. So our auxiliary function is going to be the following. So then define the function dy. It's like a difference function. That's why we call it dy. So here's what dy is going to be. It's going to be this when you don't divide by 0. So if y is not equal to f of c. If you don't divide by 0, we do that. And if, so what to do if it is equal to f of c? Well, if it is equal to f of c, then we could use the limit of this, right? Because this limit exists, right? This limit on the top exists when y approaches f of c. So it makes sense to us to define this function d using the value of the limit. So we'll use the value of the limit if y is f of c, right? And the reason, the way we define this function d, notice that we made it continuous, right? Because what is the limit of d of y when y approaches f of c? Well, the limit is precisely this, and that limit is precisely the way we define the value at f of c. So note that the limit of d of y when y approaches f of c is d of f of c. So we made it continuous. Good. All right. And then all we need to do is do more or less mimic what we tried to do before. So what is it that we want to do? Well, what is g of y minus g of f of c? Well, this is um, so I claim that this is the same as d of y times y minus f of c. Right? Now let's check it. If y minus f of c is not if y is not equal to f of c, then yes, I just took this equation on the top, this one over here, and I multiplied by y minus f of c. Right? That's all I did. Yes. But then you may be wondering, Al, but what if this guy is 0? Well, if that guy is 0, then this part will be 0. And if y is f of c, then these two are the same as well. So this is good, even if y equals f of c. So this is correct. Correct, even if y equals f of c. Okay, and then we can divide by t minus c. And plug y equals f of t. So let's go slow. Let's first divide by t minus c. Right? And then we, instead of y, we plug f of t. So g of f of y minus g of f of c divided by f of, t minus c equals v of f of t times f of t minus f of c times e minus c. All right. Okay. Now we can try to do the limits that we tried to do in the first place. And can we use the algebraic limit theorem or not? This on the left is exactly what we want. That would be the derivative that we want to show it exists. This one over here, we know it exists when t approaches c because it's the derivative. Is the limit definition of the derivative for the function f. And this one, d of f of t, well, that's the one I wrote over here, right? D of f of t, the limit when d of y, when y approaches f of c, is d of f of c. So it works perfectly as well. This function d is continuous. So from here, by the algebraic limit theorem, we can do the limit when t approaches c of this as the limit of d of f of t when t approaches c times the limit of f of t minus f of c over t minus c when t approaches c. Each one of these limits exists, so the limit of the product is a product of the limits. Now this over here, we calculated it before, is the limit of d of f of c is precisely g prime of f of c, right here at the top. When you do this one, d of f of c is g prime of f of c. So this is g prime of f of c, the way we define it, times f prime of c. And that's it. So it means the derivative, the composition function is differentiable at c, and more than that, it equals what we know the chain rule should be equal to. So it's g prime evaluated at f of c times f prime of c. All right? Okay, so this sort of finished the important properties we want out of the derivative, right? From here, you can now essentially do everything that you did in the regular calculus semester when you learn about derivatives for the first time. And so now we want to go back to that question about if the derivatives can have jump discontinuities. And so first of all, we can keep talking about these functions g's, right? And they are nice in the sense that you can use them. There are a few exercises in the book that are about that. And you see, for example, 5.2.7, I believe. Yes, the problem 5.2.7 in our book, which, by the way, I think it was featured on our final exam last semester, in at least part of it, tells you about how we can construct functions that have maybe the first derivative and then the second derivative, but not the third. Or maybe the first, the second, the third, but not the fourth, and so on, right? And the functions that are featured are, once again, these functions that we were talking about, the functions gn, like this one over here, right? So the one you see on the screen right now is one where we saw that the second derivative exists. So this one has a slope of 0 right here at 0. But the second derivative, I'm sorry, but the first derivative is discontinuous, right? The first derivative is not continuous. So can we make the first derivative continuous? And the answer is yes. You just need to go to the next one. If you look at the third one, is now the one you see over here. So now is G3, right? This G3, it from the picture, it doesn't look different from G2, right? But these functions that are now bounding these functions that you see over here are now 2 cubic functions. So if I were to maybe try to do it, if I were to try to draw the boundary here, this one over here, these are actually cubic functions. So like this one here, this is x cubed. And the other one, I'm not going to draw it because it's too difficult. The other one, the complementary one, is negative x cubed. So that we oscillate between x cubed and negative x cubed, right? And this function over here actually happens to have also a first derivative. So this is differentiable at 0. The slope is 0. But this time the derivative is continuous. This time the derivative will be continuous. And then you can ask, well, what about the second derivative then? And the second derivative will not exist. So this is an example of a function that has a first derivative that is continuous, but the second derivative doesn't exist, right? And then you can keep going, right? So you can go to the next one here. You can look at the fourth and so on. So we can close this. You can go the fourth, the fifth, the sixth, the seventh, whatever, right? And the only issue is you need to, well, the pictures are harder. It's harder to see what's going on. Like right now, you see my picture is not telling me the truth. I need to really look for very small values, right? And right here, we're already looking into the millions, right? So we're zooming already 1 million times to see what's going on. And it's not the precision of Mathematica that I have right now doesn't allow me to see what's going on here in a clear way. So this graph is obviously doesn't have these sharp turns that you see here. This is just Mathematica not being able to calculate with the precision that I need. Well, like I can fix it. I can add more precision and then it will be able to do it. But just to let you know that the pictures become harder and harder, but the analysis that we could do will not. So this is what we're going to be picking it up next class. So we'll pick it up from here and we'll prove a theorem called Darboux theorem, which will answer a question that we left hanging, meaning, can we get a derivative with a jump discontinuity? All right. So I'm going to stop shortly unless any of you have any questions.
Just a question about the exam.
Yes.
Are we going to get a copy of the exam? I'm just talking about the first exam, the one that was graded. Are we going to get a copy of our graded exam since we're not going to see you anymore, like scanned versions or?
Yeah, someone asked me about that before as well, and it's I would like to, but I don't have. I mean, as it is, I'm already behind on all my grading, not only with you guys your own class, but the other class that I'm teaching. So I don't have the bandwidth to scan all the exams and then upload them. But if you want to look at your test, you can come to office hours. I haven't had any people around, and I can show you your own exam.
Oh, okay. So we still have actual, but office hours via Zoom, you mean, right? Is that what you mean?
Yes.
Oh, okay, okay, okay.
Yeah,
Okay,
you can project your own exam, and you can take a look at it. So,
okay. Perfect. Thank you.
absolutely. Other than that, maybe I can give you that maybe not be as hard that I can record what you got on each of your so give you your partial scoring. That can be a possibility. So that's as most as I can do, right? I give you a list of what score you got on each of the problems, and eventually also I will post solutions to that exam. I haven't had the chance yet.
Gotcha, gotcha.
And the exam. So the other question is it possible to set the exact date for exam number 2? All right. So right now we have it on the schedule when
On the 23rd.
23rd. Yeah. So I am somewhat flexible. So yeah, let me think about it, and we'll discuss it next class. Mhm. But we have some flexibility about the date. It's not that important to me right now. Mhm. All right. Anything else? Okay. See you guys in a couple of days. Stay safe.
Thank you.